Welcome back to another HVAC-Engineering-Techie training video. Today's training video is the first one on building enclosures. Now, building enclosures is not one of the mechanical systems, but it is one of the systems we have to commission. So I've gone ahead and built these series of videos to explain what enclosures are and how we actually go about commissioning them. So today's video is on building enclosure systems. It's a systems video and explains the different components you have to look at and how you do design reviews and that sort of thing. And then we'll have later videos that are on actually how to commission videos to keep them being too long. So remember, this is the channel that talks all things building systems, HVAC primarily, but also electrical, plumbing, and all the other systems. And now today, including building enclosures. So thank you very much for watching the videos. I really do appreciate it. Thank you very much for being a subscription member. If you've not subscribed, boy, I'd really appreciate it if you did. It's totally painless. It's totally free. It costs you nothing. No one will bug you or anything. You just have to hit that subscribe button down below. Give me a thumbs up if you like the video. Those don't cost you anything again, but Google uses those to evaluate the videos, which I appreciate. It keeps me on the air. Thank you very much. Let's get started on building enclosures. So the first thing we're going to do today is take a look at those other videos I told you that we have for in the building enclosure modules. And we see the first one is E9. It's how to specify building pressure testing. It's designed really for engineers and architects to understand what they have to specify to get a building enclosure, but it also describes building enclosures. It doesn't exactly tell you how to do them. I may do a video on that in the future, but this E9 will help you understand building pressure testing. S-30 is this video where we're going to talk about all the different systems that go up to make up an enclosure. CX18 is the technical CX in building enclosures. It's the first one. It starts down the road of how we actually commission building enclosures. And CX19 is building enclosure commissioning, design review, and site inspections. I broke those two components out because they're the most critical, and they would have been way too long a video to have them both together. So they're just two separates and the same, but tell you all about how to commission an enclosure. So the purpose. This training video is provided for general knowledge of building enclosures to assist engineers and technicians who are involved in building engineering, commissioning, or construction of commercial buildings. It is not intended to be a resource for architectural or structural engineering guidance or practice. That's way beyond these videos. These videos are just trying to get you familiar with what you need to be looking at. Now, enclosures are not hard to do. They're a little more difficult than mechanical systems, only because you're less familiar with what you have to do, and you have to be present much more during this period than you do to a mechanical system. And we'll go through all that, but it's really common sense. You know, if you're a guy that can work with your hands and you understand that, or have been working with mechanical systems, you can figure out how to do an enclosure. It's just a little bit different, and it'll have to take some time for you to get used to it. The video concentrates on building envelope components which provide the energy efficiency of the building. The building envelope must be capable of providing the following for an efficient, safe, and comfortable building. That's rain, snow, and ice barriers, air and wind barrier, vapor barriers, thermal barriers, solar barrier, sound barrier, safe and secure from natural disasters, and safe and secure from man-made disasters. So these are the things we're concentrating on. There's a whole bunch of others, architecture, but we're not getting into that. It's, the architects inspect and police their buildings based upon visual. So they look at everything, and if it looks like what's following their schedule, that's what they do. Well, we go a little bit deeper in that we're talking about the enclosure and how those things all work together to provide an efficient building. And you can't do a lot of that stuff just by sight. It has to have some knowledge and inspection. And like everybody else in the construction industry, architects have always assumed that if you build it and it looks okay, it's okay. Well, it may not be. And we provide that by actually providing some testing of the enclosure, which proves it works or it doesn't work. So this is a learning experience. If you want a job and you're commissioning your first job, the contractors have never been commissioned before, you both have a learning experience because they have to learn how to actually build a building that will actually be efficient, and it's not by sight. It's by knowledge. And so once you've done one, and once a general contractor's done one, he gets better at it. And he does two or three, he gets really good at it. It's not hard. It's just they have to pay attention to different things than they pay attention to. And that's why commissioning is so important, because you kind of help them pay attention to the things that are critical before they fully understand that they need to be doing that. So definitions. Air barrier, that's a material that retards air movement to the building or envelope. Building envelope, that's the architectural and structural components that provide the building outer barrier to the ambient elements. Now, one thing we'll bring up here is that when we commission a building, we do not commission the structural ever. Unless you're a certified structural engineer with a PE stamp, then you can do that. But otherwise, do not. And the reason is because structural carries a lot of liability. And you want to tell them what's wrong with it from a enclosure point of view to stop thermal and water and stuff like that getting in the building. But as far as the structure itself, that's far beyond our scope of work. A curtain wall, that's a frame wall hung from the structure, or it might be another kind of wall that's hung from the structure. In other words, it's not a supporting structure itself. A glass curtain wall is the same thing. It just has to be all glass. And when you see those all glass buildings, that's what they are. They're all curtain walls. Solar heat gain coefficient, that's the ability to control heat gain through a window, is measured in terms of solar heat gain. That's an SHGC, or shading coefficient, SC, of the window. Structural element, that's a component or piece of a structural system. Thermal insulation is a material that retards thermal transmission. U factor, that's the factor of a window assembly, represents or wall, and it represents its insulating value. Vapor barrier, a material that retards water transportation through the building enclosure. Now, vapor is a much different animal than temperature, and a lot of people are really not familiar with vapor. Vapor will go against airflow. Vapor will go against temperature. It has its own kind of vapor pressure, and it's much stronger than like air pressure. It'll go right through stuff. So that's why we talk about vapor barriers. Vapor barrier is a material that is not capable of transmitting moisture vapor. And that's very important, and we'll talk a lot about that during our series. Visible transmittance, VT, is an optical property that indicates the amount of visible light transmitted through the glass, also referred to as visible light transmittance, VLT. It affects energy by providing daylight, which creates the opportunity to reduce electric lighting and cooling loads. So outside light is not a problem as long as we try to get the U value high enough and still keep the visible transmission. And we'll talk about that in length. So we're going to look at these kind of structures: main structures, substructures, walls, roofs, windows, and doors, and shade structures and security structures. These are all structures that help us get to that goal, the goal of trying to keep the building efficient and safe. And that's what we're trying to do here. So main structures. Commercial buildings, now we're only talking, we will brush on residential every once in a while, but mainly we're focused on commercial buildings. We're going to look at wood frame, concrete and masonry structures, steel frame, steel superstructures, and for the first one, the wood frame building types, we have residential, which are predominantly built out of wood, but we are seeing to get some more built out of steel. And of course, they've always had masonry around. We have multiple family residential. We have light commercial, which could still be wood frame. As a matter of fact, there's a renaissance for the last 10 years of wood construction. And that is because they've been doing a lot more structural things with wood. So you'll see a lot of hotels that are 3 or 4 story that are all wood. And that's unusual. Normally we would see a steel frame or a concrete frame or a masonry frame and this wood used to infill around it. But nowadays we're seeing complete buildings built out of wood, which my only question is that normally those are light buildings, so they're not thermal as efficient as a high-mass building, and we'll get into that. They probably will not last as long. It's much harder than you think to build a building that'll last 100 years. Now, we have wood residential buildings around that are much older than 100 years and made out of wood, but they don't provide the same modern characteristics of a residential building. So wood is good. I like that. It is, but it does have problems. And so you can use wood for infill for steel or concrete frame buildings. Like this is a hotel that's going up, and you see that it's got masonry and it's got masonry structures for the elevators and all that stuff, and then wood around it. And that's fairly common nowadays. Industrial special use buildings, not many industrial buildings built out of wood, but a few are. And the options for wood are basically masonry wood frame integrations. So like this one, you have it integrated with masonry. Or it could be a steel structure and you have wood around it for wood structure. Prefabricated panels. Make it fast. If you prefabricate these wall panels and put them together, you can construct very fast because you can prefabricate the panels off-site. So what about concrete structure buildings? We have high-rises, of course. Now, most high-rises are steel because of weight. Concrete's much heavier, but you can still do concrete. Most commercial buildings are concrete or masonry. Industrial, and of course a lot of industrial can be poured concrete. It can be masonry poured concrete integration, both. It can be prefabricated panels or tilt-up. There's two different things, but I mean, you can do it with tilt-up. This is a tilt-up where they pour these structures on the ground. Have you ever seen a tilt-up? They come in and pour the floor slab for the building, and then they start building forms on top of the slab, and they pour these wall panels on the slab, and when they're cured up, they bring in big cranes and stand them up and weld them together. They're welded with weld plates, and then they'll come in and build a steel structure on the inside that actually holds these walls upright. But it's a very fast way to build an industrial-type building. Some office buildings are built this way. It's very fast, and it's probably economical. I'm not too familiar with the costing of building these buildings other than general square foot cost. So this is a pretty common method. And then, of course, curtain walls can be concrete. Concrete's kind of unusual mainly but it can be masonry. Steel frame buildings, we do see some steel frame for residential. And this is fine because they're much more fireproof and termites don't bother them at all, which is kind of a good deal. However, they do have a couple of problems. Having followed this and been involved in a few, is that they do make noise. So what happens is the contraction and expansion and contraction of a normal building, like your home. If you're in your home, you'll hear it crack, creak every once in a while. That's because it's expanding or contracting. Well, metal buildings squeal when they do that. So they normally come in and put pieces of small layers of rubber between the plates so that the wall to ceiling plate doesn't make sound. It can still move, but it doesn't make sound. So it's a little different. You have to pay attention to sound on these. The commercial, of course, can be metal frame buildings. Now, normally we see these as red stud. What we call red stud, it's a black steel that's been coated with a zinc coating or a lead coating, for resistance to rust. Or it can be galvanized like these, but the red lead is a thicker metal than the galvanized. And it can be industrial, which is a total metal building. The option for this normally is wood and masonry integration, just like the others, and steps the other way around. Wood integration, steel frame, or metal-clad engineered buildings. So you can have a total engineered building. Steel superstructure, most all high-rises are steel superstructure, and that's because of the weight to strength ratio is much better than concrete. Concrete's very strong, but it's very, very heavy. So the higher you build, the bigger you got to build all the members because they've got more weight on them. Commercial. Most multi-story commercial buildings are made out of steel, as well as most industrial buildings, because the industrial buildings are supporting other things, like this one has a crane reel on it. Steel works better for that kind of industry. Options are, of course, steel frame and masonry integration. You build a steel building and you fill in the infill with masonry. What happens to a lot of steel high-rise buildings is they build concrete for the lower area, structure support, and everything above the first or second floor is all steel. And they do that because they can use the mass down below, and then so it's a good combination. Prefabricated wall panels are certainly possible, and curtain walls. Most steel superstructures like high-rises use curtain walls everywhere. All right, the first structure we're going to talk about is substructures. Now, if you've not done much of this, you might say, well, what do we have to do with a substructure? Well, substructures have some areas of concern, and that's footings and stem walls and slabs, and we'll talk about that in a minute. But this is a typical, remember, in architecture, architects build things many, many different ways. So everything I'm going to show you in this video is a way, but not the only way. But there's similarities between all of them, so you'll get what I'm trying to talk about here. This is the footing for a wall, and this is the device that provides the support of the building by the area of this bottom foot here. It also helps with the uplift of the building because it's covered with earth here, or compact material. This is a stem wall, and this is what gets the load, carries the load from the actual building wall back down to the footing. It's called a stem wall. And this is, you'll see the things we're concerned about. We're concerned about an insulation barrier. We're concerned about cladding and vapor barriers and water barriers. And then we're concerned on how this all goes together. And right here's the key. How does this look? And we always want a barrier right here between the wall and the stem wall, depending on what kind of wall it is. And they make seals. They make special seals for here. Now, if this is a masonry wall, you might think, well, that's not necessary, but it is, because just because this has grout here, believe it or not, the grout may be porous to air and vapor. So we'll need some kind of seal to make sure that that is sealed. On a frame wall, it absolutely needs a seal. I mean, I learned this the way by doing building pressure testing. I mean, I've pressure tested buildings. First thing, we take them negative, and you see dirt or dust all around the floor at this seam because it's sucking air underneath the wall. You don't think about it, but it does happen. So we need a plate seal there. This is the insulation, and then this is a vapor barrier or air barrier, and we'll talk about that at length later. And this is a cladding on the outside. This happens to be brick, and this happens a lot of times, and there's special things to do with brick, which we'll talk about. There's flashing, and there's cladding wall protection underneath it to protect this from the dirt line. And then down below, we have a weak trench drain system. So that if water gets against a building, this trench drain allows it to drain away from the building. One thing we want to pay attention to on our sites as we do them is that these walls or these stem walls are not washed with water. Landscape water, if you let a sprinkler system sprinkle on the wall, it'll eventually destroy it. Water's aggressive. Water's normally acidic. So it can destroy the building. So you want to make sure that you look at the sprinkler system and the landscape watering system. Make sure it doesn't flood water or spray water on the walls. That's very important. So we're going to look here at the water channeling, the vapor barrier, the thermal insulation, and the waterproofing to make sure this is 100% waterproof. Substructure types. We have floor slabs. Now, floor slabs have vapor barriers also. Now, remember, we're not dealing with structure, so we don't really pay attention to the rocks below, but the architect does. He has a certain grading. He wants rougher material down here and finer material up here. But what we do care about is the vapor barrier and the insulation barrier. Now, with modern structures, most floor slabs should all have an insulation barrier and a vapor barrier below them because we don't want moisture coming up through to that slab. I've been in several remedial situations where we have damp slabs that are growing mold because they have groundwater coming up through the slab. I've spent early in my career as a hydraulic engineer, and you don't understand that it doesn't seem plausible that groundwater, you can be 100 feet, 500 feet to water out here outside the building, and all of a sudden water's coming up through the slab. Well, hydraulic gradients in the earth are not level. You think of water being like the sea, where the sea has a level. This water in the earth does not. There's different things happening that push the water up or lower it down, and it can be anywhere. So almost all slabs need to have some kind of water barrier and an insulation barrier. So we look at vapor barrier, thermal insulation, expansion joints, contraction, cracking. Concrete will shrink and it will crack. So there has to be either expansion joint material in it or crack methods to get it to crack in the same place. It's another reason why we want a good vapor barrier down there, because the concrete will crack, but the vapor barrier needs to be such that it will stay there. So normally what we have is one it'll allow the concrete to slide back and forth between the insulation and the vapor barrier, and the vapor barrier stays set. Radiant, if you have a slab that has radiant piping, whether it be heating system or cooling system, you need to make sure we understand what kind of depth it has. It's very important for radiant that it be within 2 inches of the surface, not buried down here. We want the heat to go that way, not that way. All right, walls are the main subject normally on a building because they're the ones that are the hardest. So wall types, we have wood frame, built up or prefab panels. You can do either one. Steel frame, masonry. This can be made from brick, stone, or concrete block. It's considered masonry. Poured concrete. Veneered walls, which are basically got cladding on the outside and made up from different components. Non-structural outer layers, such as a brick veneer. We have tilt-up panels, we have precast walls, we have curtain walls, and we have glass curtain walls. And these are the type of walls we're going to look at. And we have storefronts, which are basically a curtain wall. The wall function is the load-bearing walls. They carry the load of the building. So they basically carry the weight from the floor, upper floor, down to the stem wall. Non-load-bearing walls are infill walls or partitions or curtain walls that just enclose the space but don't provide structural support. And shear walls are a wall that's put in the inside of the building that helps the lateral stability. So it's designed to resist lateral forces of the wind and earthquakes. Now, you don't get involved in those because they're not part of the enclosure. They're just part of the wall. But just so you know what they are and why they may be in a building that looks kind of different, you may see a wood frame building that has a concrete wall, poured concrete wall in the middle of the building. Doesn't make any sense. Well, it's a shear wall. And part of the new wood frame structure is with what they call shear panels. They make prefabricated shear panels now that are made out of solid wood material that allow it to be shear walls on the building. Retaining walls, engineered to resist lateral pressure from soil, often used in basements and parking garages and things below grade. They have to be a lot stronger to be able to take that force of the earth outside. This force is pushing against it. Curtain walls, of course, are non-bearing load walls that are actually hung from the structure. And we'll talk some about that because they can cause a lot of problems later on in the structure. So one of the main problems with building enclosure commissioning and construction is they're made of many layers. And those layers are all built by different contractors. So you have this myriad of contractors on this job. And as a commissioner, you have to watch each one separately as they go together. And because that's how we do that is by inspection. So we're going to look at all these different levels. This is a steel or wood frame, this is steel frame wall. And these are the components. First, we're going to take care of rain and snow and control layer. So we have a cladding, exterior cladding, that's designed to prevent that snow and water from coming into the building. We have an air control layer, which is the air barrier. Now, remember I told you that architects can build a building all kinds of ways. So, I'll teach you the general stuff, but it can be much, much different. So you have to kind of dig your way through it. One of the biggest things we do in design review is to try to find out where the air barriers and vapor barriers are. Many, many times I've asked an architect, explain to me your theory on a vapor barrier. Where are they? And you'll find out there's no vapor barrier at all. Because the easy way out, unless you're building down south where it's really humid, but if you're in a mid-climate, Midwest, West, you can get away with no vapor barrier at all. What it is, the water comes into the wall structure, penetrates it, and then as soon as it gets dry outside, it goes back out. And they can go in and out. But the problem with water barrier, the water inside the wall, is as soon as it's captured, if it's captured and it can't dry, it will grow mold. Absolutely will grow mold anywhere in the world. Because all over the world we have mold spores in the air. So if they get trapped and the moisture's there and the temperature's right, they will grow mold. So we want no wet material inside the wall. We want the wall to be dry. So we either protect it from getting wet or we protect it so we can release the moisture back out, so we don't want it to stay. So the holy grail is never, ever have two vapor barriers. If you have two vapor barriers, whatever's between them is trapped and can't get out. And that's where we have serious, serious mold problems. So you have to be on the lookout of that because some architects don't pay any attention to it. I don't know why. I don't understand that, but I'm dumb enough to say I can't see your vapor barrier. Where is it? And if they don't answer, which a lot of times they just don't answer, you understand they don't have any, so you have to pay attention to that. Or many times they'll do a really good job about vapor barrier, and the cladding happens to be a vapor barrier, like steel. And the minute you do that, all of a sudden you have two vapor barriers. So you have to be fairly careful with that, and you have to explain that to people that we can't do that. So the air control layer is very, very important. And then we have water control vapor barrier, which is important also. So here we have insulation on this wall, so we have cladding, and then right here we show insulation, and then we show a vapor barrier, air and vapor barrier. So you can buy material that is just an air barrier, where it will let vapor go through it, but it'll retard air. Now nothing's perfect, so you can't get a perfect air barrier, but you will get one that retards air a lot, but it'll let vapor through it. Normally, they're air and vapor barrier. When they're a vapor barrier, they're also an air barrier. So they have to be one or the other. And the insulation you put up here, like this insulation in this blue, it can be permeable or non-permeable. So if it's permeable, it means it'll let water go through it. If it's not, it's actually a vapor barrier. So you have to pay attention to that. Now, it's okay to have two vapor barriers attached to each other. Like if you have an insulation barrier that's foam, which is closed cell foam, which is a vapor barrier, and you have a plastic vapor barrier behind it, it's okay because water can't get between them, so you're in good shape. And then we have a wallboard structure board, thermal control layers in here. We have insulation here, or we have it on the inside. And then we have a structural layer, which is the stud walls here. And then we have a sound control layer, and sound control is always mass. So if you have a stud wall like this that has absolutely very little mass to it, and you need sound in it, then what you do is you start building up drywall on the inside. You do a double 5/8 layer of drywall, which is mass, and it will retard the sound layer between the walls. Now, how do you know what's going to be a sound problem? Well, you have to be a lot smarter than me to do that, even though I used to be a sound measuring guy and went through all those certification courses to figure out how to do sound. I still am not an acoustical engineer, which that's a very difficult science to understand how to propagate sound and understand what's going to cause a sound. My job was always fixing it after it happened. So I could go measure the sound, figure out where it's coming from, and figure out a remedial source. That's fine, but to figure it out ahead of time, it takes a smarter person than me. But some things are obvious, like if you have a screw chiller sitting outside a wall within 4 feet, and it's not soundproofed, it'll go right through that wall, and you'll have problems, that kind of thing. So you get it. And then also we have this other wall that has a brick cladding on the outside. It's just an exterior cladding. This cladding may be a board, maybe steel, maybe stucco, could be whatever you want on the outside. This one happens to show brick, but it's the same consideration of where you put the different parts of this wall. So, concrete walls. So, okay, concrete walls are the same thing. They have an outer layer. Now, why would we put an outer layer on concrete? Well, concrete is not waterproof. This is one of the problems you have in architectural components. We have a lot of preconceived notions about what is a vapor barrier, what is an air barrier, and how is air stopped and how is water stopped. And boy, a lot of it's not true. Concrete will absorb moisture, so you have to do the same thing. It also is not that hot a temperature. The one thing it is mass. So what happens in a concrete wall, and we'll go over this in a minute, but as you heat the outside, it heats up the concrete, but it does it really slowly because it's got a lot of mass, and that's what's important. So we have a rain or snow control layer, same as the other. So we have a cladding on the outside, and it might be stucco, it might be a board, it might be metal, it might be some other material. We have an air control layer, and that's behind it. This would be the air barrier. We have a thermal control layer, which is the insulation here. And then we have structural layer, which is the concrete itself. And we have sound control, which is the concrete itself because it's got mass. Now, you notice these two look different. This one's got the insulation on the outside. This one's got the insulation on the inside. What's the difference? Well, unfortunately, normally you see them built it this way, which it really should be built this way. And then we'll get into that in a few minutes here. But what happens is this wall is coupled to the interior. In other words, this mass is coupled to the interior because the insulation is on the outside. This wall, the mass is coupled to the outside because the insulation's on the inside. Now, the reason we build them this way is because it's easier. It's harder to put the insulation on the outside. It's easier on the inside, but this one is far superior thermally, and we'll go through that and prove that to you and show that. So here's a wood frame wall, which is a light wall, and you can see it's got the same thing. So on the outside, we have to have some kind of rain or snow control layer. It's normally could be stucco, it could be siding, it could be brick, it could be all kinds of things out here, but it needs to have a rain and snow barrier. These have an air control layer, which on this one is hard to see. It's pretty small for me anyway. That would put an air barrier right there, and a thermal control layer, which would be insulation on the inside of the wall. Normally it's batt on the inside of the wall, but it might actually be an external plastic insulation layer, especially if it's got stucco, it'll do that. It might have both. And it'll have a vapor layer. If it has a vapor layer, it might actually be on the inside of the wall, or it might be on the outside of the wall, either way. And we'll go through what those are. Fluid applied membranes. Now, these are vapor barriers and air barriers that are sprayed on instead of rolled on. There could be self-adhered peel and stick membranes like this. This is called a house wrap, and it basically sticks and peels. Now, I'm not a big fan of this stuff. It's okay. The material itself is really good. That works great. But the problem is the installations are normally poor. And they leave sags, they leave gaps, they leave protrusions that are unsealed. And so it basically doesn't do a good job because of the way the installation's done. And another thing, if you get the back of this dirty, it no longer sticks. And I've seen that a lot, where down near the stem walls, it's coming off because it's not sticky anymore. So I'm not a fan of this, but it's used a lot. Mechanically fastened membrane, which is this one here, which is basically the same as, it has a different name on it. It's basically the same material, maybe a little thicker. And it's actually put on with nails with improved this material as the head. So basically it seals right where you put it in. You can see these little black dots. And this guy right here is putting a special membrane on a window opening, which they have those which are glued on. You have that. And it could be rigid sheathing, like a wallboard with tape seams taped, and then they put cover it up with whatever they're going to cover it up on. Or it could be spray foam. The closed cell spray foam is definitely a vapor barrier, and that can be sprayed on wall surfaces. So these are the different kinds of air barriers. Now, on an air barrier like this one, when they're spraying it on, which is very common, and actually it's a really good air barrier. The problem is it's not a good air barrier if you don't get it sprayed on or you don't get it on thick enough. So especially on masonry walls. On masonry wall, it has to have a very thick coating, because what happens, it'll have little air bubbles that expose the concrete block below it, and the concrete block absorbs moisture like a sponge. So if it's sprayed on insulation, your inspection has to be that it's on thick enough, because the installer is just spraying it, and he normally washes it like paint. Is it the right color? I'm okay, but it's a thickness problem. You have to inspect it. Fortunately, you have to inspect all of it. You can't just inspect one piece and say it's right. It might be good here, it might be not good over here, so you got to look at it all. Vapor barriers, okay, polyethylene plastic sheet, polyfilm, and you'll see residences that have this plastic sheet on the inside. That's actually a vapor barrier. It could be foil faced or craft face. This craft face is a retarder, not so much that. Now, the discussion would go on a little bit. When should you have the vapor barrier on the inside, and when should you have it on the outside? And that's a discussion the world has had for 30 or 40 years. So don't feel bad if you don't know which, because most of the world doesn't know. You can also have fluid applied. So you can fluid apply a vapor barrier, or you can use spray foam inside or outside. Closed cell spray foam is a great product, and why I like it so much is that it seals as it protects for vapor. It also seals airtight. So if you want a good building that's going to pass an air test, spray foam is the way to go. Now, it does have a problem. You have to deal with this problem, is it does outgas certain gases that are not desirable. So you have to, once you put it in a building, you have to air that building out for several weeks. Don't cover it right away, because then you may have this air quality problem inside the structure, especially if it's a residence. They recommend at least 2 weeks of uncovered foam to outgas prior to covering this wall with sheetrock. Rubberized asphalt or sheet membranes. These are normally done under slabs, but they're basically rubber or a plastic that puts underneath there, like visqueen. And it's a vapor barrier, and it's easy to install, but it doesn't stick, so that's why we use them on flat planes, because they're easy to put down. Or it can be extruded polyethylene sheets, polystyrene sheets, which are these sheets that you put on the wall that are actually insulation with taped seams. It's very, very important if you're using it for a vapor barrier that they tape the seams, or if not, vapor will go right through it. So that's important. Okay, let's look at heat gain. This is talking about mass and where the mass should be coupled. So here's a wall in the heat gain. So it's in a summer condition where the interior is colder than the outside. So the heat coming in from the outside hits the insulation barrier if it's on the outside, and it begins to penetrate the insulation barrier. Now remember, insulation does not stop temperature, it retards it. It slows it down. So it slows it down, and eventually the heat will get through the insulation eventually, but it slows it way down. So if you slow it enough, then it gets colder at night. Then that heat goes the rough direction, so it never gets to the insulation in that case because it's slowed down. And then you'll see the heat changes and it gets colder as it goes through the wall, these heat lines, till it gets to the inside of this concrete wall, and then it radiates or conducts into the interior space. But you'll notice it's a lower temperature. And that's why we like these mass walls, because it takes the heat, absorbs it, and slows it way down. So our goal is to slow it down until nighttime, until an unoccupied period. So you got to be really careful about this. You have to design your walls to not be too thick, because that could be a problem. You don't want the wall so thick that it gains the heat from the previous day and releases it right at peak temperature the next day. No, you want it in between that. So about 8 hours is what we're 8 to 10 hours is what we want. So that's normally a 6-inch wall. So when you get to 10 or 12-inch walls, you have to figure that out because you get too big. So the mass wall benefits, absorbs heat and releases heat slowly over time. Time delay allows for a lower peak cooling load, and this is really critical because you have a high mass building. Your units do not have to be as large. Your air conditioning system can be smaller in size. It has to deal with the same amount of heat, but over time, the peak is not as high. The radiant absorption improves human comfort perception, and it absolutely does, because that wall is absorbing heat both from the inside and the outside, and it makes humans feel better. Mass lowered sound transmission. So these are all benefits for this wall. So here's a wall in heat loss. So in a winter condition, what happens in this condition? Well, in a loss, again, the interior wall heats the interior temperature heats this wall up, slows it down, and then it hits the insulation layer, vapor barrier and the insulation layer, and it slows it down further. So basically, this hot temperature keeps getting colder as it goes to the wall until it hits the outside. So it's exactly the same as in the opposite direction. The benefits of a mass wall next to interior space: absorbs heat and releases heat slowly over time. Time delay allows for a lower peak heating load. Radiant heat improves human comfort and the mass sound transmission. So it's a win-win situation if you can build a wall like this. Now, the problem with this wall, of course, is expensive, as all things in life. Right? If it's good, it's costly. So anyway, here's a wall mass size. Mass should be sized so the time delay of thermal saturation is not over 8 to 10 hours. That's because we want to get it into a non-peak period. The goal is to absorb the heat so it can be removed or replaced at the even rate over one night cycle. Wall mass placement. Mass that is coupled to the ambient will hold the ambient temperature over time and moderate and release to the next layer. Okay. Mass that is coupled to the interior will hold the interior temperature over time and modulate its change from conducted temperature, thus limiting the instantaneous HVAC load, requiring a smaller, more efficient system. I've already said that, but that's true. Now, I actually found proof of this, which is really good. It's the first time I've actually found this study, and we're going to go through that. So I don't know, you can't read this study, but anyway, this is a thermal performance of the exterior level whole buildings at the 12th International Conference. It was done by Cheryl Sladana and Joseph Phelan. And this was a good study because it actually looked at this wall in a mass wall placement. So what it did is it took 3 walls. It took a lightweight wall like this, which is a frame wall. Still a good wall. It's a frame wall. It took a mass wall interior insulation, in other words, a mass wall coupled to the ambient, and then a mass wall coupled to the interior. And it ran computer models on these 3 simulations with all the same input and the same weather data, and plotted the results. And then, of course, it plotted the results for all these different. This is an ASHRAE standard climate zone map, so you can kind of pick out your area where you're at, and you can see what climate zone you're in. Here's the numbers. These are too small for me to read, but if you blow this up, you can figure out what these are. My area is down here, of course. And here's the results, which this is really good. It tells me now what this is the energy efficiency savings on these 3 different areas. They picked 3 different areas, and this is the window to wall ratio. So how many windows does it have? If it has very few windows, then this is much more efficient than if it has a whole lot of windows, of course, because windows aren't a wall. And the same for these 3 areas. This one here is the red. This is the deep south. This is a high humidity condition. This is the yellow and brown. This is the west and northeast. So this is the coal country. And this is the northern Midwest. So this is basically anything that's not humid. And so the difference, what these three lines are, is this bottom one is the wall coupled to the interior, a mass wall. This one's a mass wall coupled to the exterior, and this is a lightweight wall. So in every case, you can see that the interior coupled is better, and the light wall is the worst. And this is actually for energy efficiency, transmission of heat through the wall. So this one's really impressive. This one to me is impressive. Of course, this is where I live. So it says it's not much, but it's still better. It's always better. So I preached that for many, many years, is that it's best to build a mass wall. And especially if you're pressure testing a building, a mass wall building works much better than a frame wall. So if you're trying to get down to 0.10 leakage rate, I hope it's a mass building, because it's going to be hard getting it there otherwise. So this is a really good information to have, to know that these mass walls are important if the building really wants to be sustainable. Now here's the moisture thing we were talking about. So this is a wall with low interior vapor pressure condition. And I show a mass wall again, but it doesn't have to be. It's the same thing. So if we have a ambient high vapor pressure, which is where most places are, so we have systems that take the moisture out of the interior, and the ambient's very high moisture. So we want vapor barriers in here, vapor barrier to prevent this vapor from entering the building and the slab or whatever it is absorbing it. So if we get, during the winter months, if we get added humidity, it will come and sop into this wall, but it hit this vapor barrier, and then it redries. When this is lower, it redries into the space. So there's not a mold issue here, because the water comes in and then it goes back out. Here, the water never gets in the first place, so that's good. This is a wall with high interior, and this is unusual. You have a high vapor pressure in here and have a very low outside. Now, this would be where you have a building like a hospital or something that has humidifiers inside the building to maintain it for health. And it's low humidity out here, then you have the vapor barrier on the inside. So the rule is that vapor barrier should be on the side that has the highest moisture. And if you're down south, then it should be on the outside of the building. If you're up north, where it's very cold outside and you have very low humidity, it should be on the inside of the building. So now if you live somewhere that has both, you have a problem. You have to figure that out. But anyway, this is what it should be. On the outside, of course, any humidity gets into this wall, redries to the outside. So remember, you would never have this to be impervious, where no moisture can go through it, and then a vapor on the inside. That means this is a jeopardy where mold will begin. Mold will begin behind this barrier if vapor gets through it. So you want to make sure that you don't have two vapor barriers. But this is the rule about vapor barrier in walls. Okay, now we're going to talk about fenestration, which is windows. So typical window types are casement, which are these ones that are open up like a swing with a crank. We have single hung and double hung windows that slide up and down. We have awning type that open and close this way. We have sliding windows that open and close, and we have fixed windows, which don't open at all. So those are the type of windows. Window ratings. We have a U factor for windows. Now, we used to have an R value. However, R value is just the resistive value of the window. The U factor takes in everything. The R factor is just for the glass. The U factor takes in the whole unit, and it's the BTU per hour per square foot per degree F in our section. This is the inch-pound method. It's the same, for metric. It's still BTU. Or no, it's watts. I'm sorry, it's watts per hour per meter squared C. But anyway, same thing. It's about how much heat is getting through the window, is capable of getting. SHGC is a solar heat gain coefficient. That means if it's got sun shining on it, how much is it going to transmit? VT is a visible transmitter, or VLT, same thing. Air leakage is CFM per square foot of edge seal at 3 inches of water, or 6.24 pounds per square foot of air pressure difference. So that's when you see a manufactured window and it says air leakage, that's what it's rating, how high of leakage it actually has on that edge seal. Frames can be wood, aluminum, PVC, or steel. They can have an insulation break. If they're aluminum or steel, they might have an insulation break that prevents a lot of temperature from going across the steel into the space, or bridging we call it. Insulated frame. Glazing types can be all kinds of glazing types. 3/8 standard clear glass, we're talking commercials. So 3/8 standard, you can get 1/8" glass, but you should never see that on commercial. So normal is 3/8 standard clear glass, plate glass, and that's what we normally use. It could be low E clear glass, which means the color of the glass is such to limit the sun energy through it. Reflective surface, bronze tint glass, selective low E glass, argon, krypton, or xenon gas-filled glass assemblies that helped on a double pane or triple pane. It retards the conductance of heat across the glass pane. Bullet-resistive glass can be normally as small as you get is 1 inch, be slightly under 1 inch, to 2.5 inches, depending on how large a projectile you're trying to protect from. One thing about bullet-resistant glass is very, very heavy. Even if it's acrylic sheet, it's heavy. It's not as heavy as tempered glass, but by the way, up here at 3/8 standard glass, most of this is tempered, which means it's gone through a heat treat process where it doesn't crack. That's why you see this glass shatters instead of cracks. It builds up interior tension until it just can't take it anymore. The whole sheet crumbles. And they use tempered glass because it's stronger, of course, but second, it's not dangerous when it blows up. When a regular non-tempered glass cracks, the pieces of glass are sharp and cut very, very severely. So we use standard tempered glass everywhere. And when you buy a piece of glass for a job, you'll see them coming in crates or boxes, and they'll have something like this on the outside of them, which is done by the National Fenestration Rating Council. They also do fire safety and FPA, UL, and ASTM. And these are the different properties. Like we said, here's the U factor of the glass pane assembly. Here's the solar heat gain coefficient. Here's the visible transmittance. And here's the leakage. And condensation reference resistance, which is how resistant it is to forming condensate on the glass. So here's the different things available for glass. We have single pane glass, which is fairly normal. This comes up with a U factor of 1.25 for 3/8 standard glass, which is not good at all, actually. It has an SAGCS 0.72 and a VT of 0.71. Now, as you get to a second one with a two pane, and you'll notice that it's got clear glass on either side. This window is a U of 0.60, so we've cut this in half by going to 2, which kind of makes sense. And it has SG of 0.6, so we see that has gone down. And the VT is now 6.3 instead of 7.1. So when we start adding glass, the visible transmission go down. So it starts getting harder and harder to see clearly out of a glass. So you have to kind of understand that as you gain thermal resistivity, you lose in sight. So this one here is a double glazing, a bronze tint. It's U factor 0.60 again, but it's the solar heat gain is down to 4.2. So if you had sun shining on it, this will help because it'll distract that. And it's down to 0.42, and the visible transmission down to 0.38. So you can see this will almost cut the visible transmission down considerably. And here's another one, which is a double glazing reflective coating on the outside, and it goes down a little further. This is a double glazing low E bronze tint, so it's a bronze tint, but it's also low E. So it gets further down, so we're U factor down to 0.49 now. You can have a double glazing selective low E, which is a little bit better yet. Now we're U46 instead of 4.9. Get double glazing of selective low clear, and it goes to 4.6. Now this is a triple glazing, and you can see that the triple glazing is low E is down to 0.20, and its visible transmission now is down to 3.7. So triple, we don't see many triple pane because they're very expensive, but they do help. So triple pane. You also make 4 gain. I've never seen one of these, but I guess you could do that. Another thing that we have talked about is this is down to a wall U factor of 0.14, and 0.14 is better than some walls. So 0.15 U factor is a fairly good wall. 0.1 is a good wall, Here we have a glass pane down to what a wall factor actually is. However, its visible transfer is down to 0.34. So if you live in the tundra, northern tundra, and you have really cold temperatures, floor pane would be a good idea, but it's very, very expensive. Like I said, I've never seen one. Okay, now we're going to go back to that same study again, which I thought is really important. It actually talks about this also. Study compares mass wall building and climate zone and glazing contents. So here's the three deals again. This is down south. Now what this graph's actually saying is that this is the mass exterior insulation, mass interior insulation, and lightweight wall. So this is the one with the mass coupled to the interior. This one coupled to the exterior. What this means is that if you have double glazing in your windows versus single glazing, this is the improvement. If you do triple glazing, then this is the improvement. It's very significant. And here's this mass wall to the interior. So again, you get a fairly good with double pane, but triple pane, you actually get a lot more advantage to that. And this is the cold people up north. You can see double windows important to them. And then this is the dark glazing, which is the Midwest, which is the dry. It's still better everywhere, but significant in light wall. So, I mean, it's good to take your windows, pay attention to your windows. That's important for energy. And the wall is too, but the glass can be big because normally it's not so much glass, so you don't get as much benefit from the wall, a benefit from glass as you do a wall. So reason for different fenestration types: low thermal conductance, lower solar transmittance, lower sound transmittance. Now, one thing about the rule here is that you try to, in design, you always try to not have a sunlit window. Because a sunlight window transmits a lot of energy. When you're doing a heat gain, you have a heat gain, you got a difference of 40 degrees, and you got a wall factor of 0.15. That's all looks good. But you take and sunlit that wall, now you've got, instead of using 40, you got 158. So it's 4 or 5 times more temperature transmittance than if it's not. So we try to do shading such that the windows are not sunlit, or if they are, for a very short period of time. So window glazing. Multi-pane assemblies have a capillary tube or other vent device to protect the window during shipment from pressure changes which would damage the glass. So this is a problem. We either have a gas or we have air between the. If we have air between the panes, they have an open capillary on them, so that as the trucking company goes between elevations, these windows don't bulge out, right? Because that gas would be under higher pressure, so it actually vents the outside. And these are protected from moisture to get in there, but they do that. Now, if it's got gas inside of it, then it won't have this. It'll have a bellows device that lets it expand and contract, so it can also be transported, because transport's a problem. It's kind of like, if you get a bottle of water at one elevation, go a different elevation, your bottle makes all kinds of noises as it's expanding and contracting. Well, that same thing happens for windows. So if you have a pane with air inside of it, then you have to, as these are installed, they have to seal this capillary, because you're now at the right elevation, so you don't want moisture going in and out of there, so you have to seal it up. And normally you use silicone caulk and have sealed this capillary up. And as a commissioner, that's one thing you need to verify, that they've actually sealed up all the glass capillaries. The capillary must be sealed, like I just said, according to the manufacturer's instructions, and normally it's a piece of silicone caulk. Here's some standard default SHGCs if you can't find it on a piece of glass. These won't be exact, but they'll be close. So it tells you that here's the clear plus clear, bronze plus clear, green plus clear, gray plus clear. And this is the double pane e-glass. It shows you what they ought to be. This is the operable or fixed glass. And these would be the sensible solar heat gain coefficient. This is standard default U factors for the same. You can see this is a metal without thermal break window. Metal with thermal break, reinforced vinyl, metal wood clad, wood, vinyl. It talks about fixed or operable, and single and double glaze. These are generalizations, but if you need that, if you're trying to do a calculation for what savings would be, go from one wood to the other, or whatever, you can use these general factors. And these are from the IECC, so they're reasonable. All right, glass curtain walls. These are all curtain walls on these buildings. Glass curtain walls can be simple storefronts or can be complete building facades. Sorry, can't speak English. The main concerns are thermal transfer, water and air leakage, expansion and contraction, durability to damage from windblown debris, future replacement, exact match problems. So one of the problems with this is you get a pane that's cracked, either by thermal expansion or by impact, and you have to replace the window. Well, it has to be the exact type of glass or else it's going to look terrible. You see it all the time. Whereas they've got a real beautiful wall like this. Of course, it's in a fancy picture, but all of a sudden you see a pane of glass, you can just see it like it sort of sticks out like a sore thumb. So it's not good. You need to do that. Curtain wall basics. Okay, so now here's these curtain walls are actually hung off the structure. And you see, here's the three things we're going to talk about. Here's how it's hung. This is the aluminum frame of that window wall. And you can see it's got a mounting bracket, and it actually mounts back to a structural element. And you can see it's not actually sealed. Here's the glass out here. Well, you've got an opening here. If this is the structure that will allow sound and allow air between them, so you either have to, if they don't want that, there has to be a seal placed here. So that's important to understand. It hangs. This is a view looking between two frames that have come together, this mullion. And you'll see this is the aluminum frame. It goes together. And then they put some sealant here, and they bolt them together. And this is the glass on the outside of the building. So this is how it goes together. Here's a view of it from another direction. This is the wall, and this is the anchor in the wall, and this is the aluminum frame and how it goes together. The important thing about this is thermal breaks. And this one, I do not see a thermal break on it. I mean, you would think this is a thermal break, but actually it's not. It's a seal, because this is the frame right here, and it'll take temperature and transmit it right into the building. One thing I found out the hard way, which is strange, is that this member, which is going horizontal, this member, which is going vertical, are not air sealed between each other. So I have done buildings where I've pressure tested this inside of the building here, and the air pressure, the leak went through here, went through the horizontal until the next room on the other side. So because these go between the structure, it was a leak we could not seal. So basically we could not seal one room or the other. It had to be a lab building where we were trying to seal the individual labs. Well, this mullion prevented us from doing that. So the rule was never, ever put a lab in a curtain wall building. They do it all the time, but they should not. It is not good. It will leak between that. So if you're building a lab, don't let them put window walls in there because it will leak. Prefabricated curb mounted skylights, prefabricated pyramid built up, custom. So you can see these different types of skylights, and they're normally built multi-pane because they're trying to limit the transmission of heat. They also may have some low E glass or some other way to try to lower the solar heat gain through the glass. Green building components, visible sightline. This is a way to, this visible transmittance is important to architects depending on what they want to feel on the inside of the space. If they want to be able to look out, which gives humans comfort to do that, they'll pay attention to what the visible transmission is. It gives natural lighting into a building. I did a building one time, which was a school, and the architect was really good at figuring all this out. And I must admit that rooms that are sunlit are much more comfortable than rooms that are fluorescent or LED light lit. It makes a real difference. You might not think you might know, but you do know. Because there's something about light color. When the sun comes up in the morning, the light's red. As it gets to noon, it'll turn blue. As it gets to evening, it turns back to red again, yellow, whatever. And the human body understands that. So because we've always lived outside. So it gives you a much better comfort and actually a little more productivity to have that. Placement of windows is important where they're at. Light shelves, this happens to be an interior light shelf. You can see this is the interior light shelf. They also put light blinds on the outside to protect the glass from solar lit. But these light shelves are designed to reflect the light into the space, making the space actually sunlit, but from a balanced angle. The issues are glare. Glare is a problem. You've got to protect yourself from glare and privacy, so you want to make sure you have that. But these are all things that the architect should have been involved in, and you as a commissioner or as a constructor, I just need you to understand what they are. So doors Doors are another enclosure issue. They're a great place for leakage, so we take them. Their characteristics, again, are rainwater control, thermal characteristics, air leaks, wind and debris resistance, sound transmittance. Door ratings, fire ratings are you get a 20-minute door, a 45-minute door, 1 hour rated, 1.5 hour, or 3 hour rated door, depending on what you need for the fire containment of the architectural design. U factor can be from 0.35 to 1.25, from good to really bad, can be either way. Sound transmission ratings, STC, are from 35 to 55, and I believe that's a decibel, but I'm not sure. I think that's what it is. A ballistic is from 1 to 8. 8's a really big bullet. 1's a small bullet. Okay, so it can get steel, wood, fire rated, both wood and steel, acoustic, by doors that are designed specifically for acoustic, and then ballistic resistance, again, from 1 to 8. They get lead lined for radiation, like if you have a X-ray machine or something, or some other machine in there that's got they're lead lined, so they'll give a certain level of protection depending on the thickness of the lead. So types available: you can get steel doors, wood doors, fire rated, acoustic, ballistic, and blast resistance, lead lined, hurricane resistance, tornado FEMA rated. These happen to be a couple of these tornado doors, and what they're really designed for is have a very large impact. And I think they're rated for, you can't drive a 2x4 through it at a Category 5 tornado, which is 175-mile winds or something like that. So they're very, very secure. And not only is it just secure on the material, but the hinges and latches are all secure with deadbolt type structures that go into the wall to keep it from being blown down. So then we also can get glass indoors. You can get solid, small lits, slit light, half door, dual light, triple pane, quadruple light, full light, door pattern. So these are all different glass you can order in a door, and all door manufacturers understand what these are when you order them. And then, of course, you can get pattern doors. You can get these in wood and steel. They can be patterned. So there's all kinds of different door structures. Exterior doors, which is what we're mainly concerned about. You can get wood frame doors, especially if it's a wood frame building. Get steel frame doors. Now, steel frames, you have to kind of pay attention to these because they can be problematic. Normally, they're hollow core frames, so there's steel frames, and they go either on the inside of a structure, on the wrap around a structure, and then they can be concrete filled, where these are filled with concrete. Makes a really good frame when they do that. These are the different frames. This happens to be a slip-on frame where it slips around the wall like this, and then you screw it in here. And this would be a wood universal stud anchor, so it has a stud anchor here. And this is a punch and dimple with tube backing where it comes into a wall this way. And this is a masonry wire anchor, which this one here is built into a masonry. It goes up, and these are normally the concrete-filled ones, which work really, really well. But butter wrap frames, I went through that. Now this is door fills, seals and fills, the door side and top seals. This is a seal that goes into a kerf. So the door comes with a saw cuff into an 1/8-inch hole about 3/16 of an inch deep, and you simply stick these in there, and they have little wing kind of things that prevent them from coming out. And this seal's tight against the door, so the door closes, it pushes it against the seal. These are very good seals, and they work really well. And these are the same thing, but surface mounted, so they mount so the door comes against and pushes, and it's a good seal. Door thresholds. The exterior door should all have a threshold on them, and they should have some way of sealing. The door should have a seal on it when it closes, or they can be step seals like these, where the step seal where the door seals against this on the bottom of the threshold, because normally doors leak really a lot in the threshold, so this is a really good seal. Like if you have a room that needs a pressure differential, like a lab space on the inside of a building to the outside of a building, it needs to have a bottom seal on it. Door sides and top seals, so this is the seal. This is a bottom seal that goes against the threshold. This is another one. This is a brush. And that does it. This is really good. This is not so good, but or you can have just a rubber surface that lines it. Hardware. So hardware is another thing you have to pay attention to a little bit, depending on what's going on with the door. We have hinges. We have security hinges, and these security hinges work in that they have more screws holding them on, but they also have these steel bolts that go into the other side when they're closed. So in other words, to break this door down, you have to break through these steel bars, which is pretty hard to do. We have locking latch sets that close the door with a lock. We have locking deadbolts that improve that with adding a better bolt. We have crash bars that are a way to facilitate an exit. We have automatic closers, which close the door when it need to be, and these need to be adjusted for correct tension. Security hardware is the keypad latches or keypad electric latches. We have electric door handles like this, or we have electric latches on this side of the door. And this is all done with because we want to be able to, security wants to latch the door. We have magnets that are done by security to latch the door. This is normally a smoke door here. What it does is it holds the smoke door open, and then when it releases this, it releases the door and it automatically closes. Or these are magnets which keeps the door closed, and we turn on these magnets, and these are really powerful magnets, and you cannot open that door. I mean, it seems like you'd be able to push it open, but you cannot. And so that's how they keep the door locked. And then we have panic bars, which are automated, which this, instead of having a latch, this actually shows a latch, but this actually would be a switch, and this may be electric latch. So when you hit this crash bar, unlike a mechanical one, it's actually doing it electrically. And then of course it might do it mechanically also. And then we have electric latches that can be opened with a system or by a key. So roll-up doors. Roll-up doors are a very big problem child for air barrier testing. They leak a lot. They can be steel, aluminum. They can be insulated, so the panels inside can be insulated. They must have weather seals. If not, and we have bottom seal that seals them on the bottom. And then we have brush seals that seal the side and the top. Now the top is where the problem is. That's where they leak the most. Brushes help, but they don't cure. So you just got to understand you're going to have some leakage at the doors. They have operators. You can have a chain door operator, or you can have automated motorized operators. Roofs. Roofs are another major area of commissioning we need to do the building. You can have built-up roofs that basically put insulation down, and then they have roof on top of it. A built-up roof can have 1 to 4 layers. Normally there's 3 or 4 layers. And so what they have here is they have a board or a substrate down below the roof. We have a rigid insulation that they adhere down to the surface, either with screws or with glue. And then they'll have a cover layer board, which can be a board, and then they put that down with asphalt, flood the roof with asphalt, and put that down. They flood it, and then they put these membranes, which are asphaltic roofing material, and they'll put several layers of that, and then they'll put some kind of coating on top. Might be a white coat or might just be ballast. So these are the different layers. I showed this one detail specifically to talk about the problem of air seal. You got to understand roofs are designed to keep water out, not so much air out. And that is a problem. So when you're doing commissioning, you have to pay attention to all the expansion joints on a roof and all the flashing joints. If it's like this one has a curb and has an expansion joint back here, this material is the only thing that's the air barrier, because this flashing is watertight, not airtight. So this must become airtight, and that is a problem because most roofing guys that put this in there just shove it in there. Don't pay attention to having gaps, not sealing the corners. So this is problematic. You can leak a lot of air out of an expansion joint, even though it works perfectly well for water. It doesn't necessarily work for air. Most of this is all hot application. It can have a white cap in a high sun area. Can have ballast on it. The ballast is put there to keep the roof rated down, weight down. And it's a hot day. Hot tar roofing is miserable. It really gets hot when you put that hot stuff down. Now this is a single ply material, which is the majority of roofs nowadays, which is single ply. It can be PVC, EPDM, which is a plastic, or TPO, which is another kind of plastic. Application is normally mechanical attachment. So here's the deal. What it is, we have a roof surface down here, and we have roof insulation, like rigid insulation put down. And then we have a roofing, a mono ply, or a single ply on top of that goes down. And this becomes important on how it's actually sealed on the edges. This would be the flashing on the top. Now the membrane layer, so this here is like a steel deck. And then this would be the built-up insulation, which is rigid. And that is normally screwed to the deck. It might actually be glued to the deck, but normally it's screwed. And what needs to pay attention here is remember that this here is not just flat. They build crickets up with that, what we call crickets. They build this up to be able to channel the water toward the drains. So they build this up thicker and thinner to produce that slope. So that's one thing you need to check. I have seen many jobs where the slope goes to where a drain was going to be but didn't get there, or goes away to someplace else that there's no drain. It's really poor. So, or it doesn't actually slope to the drain. So you need to check all that out. The other thing too is important. You'll see that this is the roofing material go down, and you see it's actually adhered with a special kind of nail that has a little top on it. Does that because this must be adhered. Normally we see glue adhered, but it must be adhered. I have seen a job, unfortunately, that I pressure tested a building up in Utah, and the roofer did not follow the spec on how this would adhere. He put it down and he sealed the seams. They weld these seams together and glue them. And when I pressure tested it, they happened to have a penthouse on the building that opened this roof that you could see this in the penthouse. You could actually seal the top seal and the insulation. And when I pressure tested, I blew the roof off. I didn't actually blow it off, but I blew it 2 feet in the air because it delaminated. It wasn't stuck near enough at all. And it blew up when I did a pressure test of 0.3 inches. So it's important that it be adhered. Color can be white, gray, or tan. I'm telling you, this is the most roofs. And here's how not to do a roof. This is one of my commissioning jobs, and you say, well, how did that ever get installed like this? I don't have that answer, but what I did find important is the general contractor never looked at this roof. The reason was it's hard to get to this piece of roof. This roof did not have an access hatch. You had to get there by a pretty long ladder. I crawled up there to just see what this was like, and seen this roof and took a picture, and the general never looked at it. So this roof will fail, and the reason it'll fail is because all these bulges, they will eventually get brittle and crack, and then there will be a leak. So this is how not to apply single layer. Spray foam. Spray foam is good for flat roofs or specific sealing problems. Protective top coat. It has to have a foam. Sun will degrade raw foam, so it has to have some kind of white cap or another kind of cap. Gypsum. Sometimes I've seen them put gypsum. Liquid gypsum on it that dries hard. That's good. Also, foam is very fragile. You take a screwdriver, you can go right through foam. Even if it's got a white cap on it, you go through that. If it has a gypsum cap, you can't, but this can. So foam is a very good seal. Again, it seals tight. It seals everything, but you have to be careful with it also. So metal roofs come in galvanized configured steel, which you've seen a lot. It can be a shape like this, coated steel. It can be coated with many different colors. It can be a standing seam roof like this where they come in pans and you just crimp over the top to seal them. You put a little bracket here, the little bracket that seals to the roof. You nail it down to the roof and then seal the seam to the bracket. Very popular in some parts of the country. They are very durable except for hail. Now, hail doesn't damage the metal, but what it does is it damages the surface. What it does is when it hits, it forms a little dimple. And that dimple will separate the coating from the steel. And so eventually the coating will come off and it'll be susceptible to the ambient. So hail can destroy a metal roof. It can come in aluminum, copper, stainless steel, or color-coated steel. Color-coated steel is by far the more popular, which this is. I have done early in my career as a mechanical contractor. I became the expert at copper roofs. Did a lot of copper roofs. They're really nice, really beautiful, and very expensive, but they do work well. Slate or tile roofs, which are really beautiful. We don't see many of these in our territory, but they are possible. They can be stone, they can be concrete, they can be clay. And it's the way they go together. They're heavy. Your structure has to be built for them.
Application is very important. Sloped roofs only, of course. You can't put them on a flat roof because they'll leak. Tile roof issues are brittle. They're heavy. So we don't see many slate roofs, but you can have shingle roofs on commercial buildings. They could be fiberglass. Asphalt or Kenny map. They used to be asbestos. We don't get those anymore, of course. Have an architectural shingle, which is a thick shingle, so it has an architectural shape to the edge of the shingle. Application is sloped roofs only. Single roof issues, shingle roof wind damage is much easier for wind to damage a shingle roof because it lifts the shingle. Hail damage basically will break the shingle. And there's a skeptical length of warranties. Most of these say we have a 30-year warranty on the roof. That's very skeptical. I'm not sure I've ever seen a shingle, an asphalt shingle or fiberglass shingle actually last 30 years. What happens is the coating starts coming off the shingle as the sun erodes it, and eventually it will expose the fiberglass membranes, or the asphalt will begin to show up on it. And when that starts happening, it gets fragile, and any hail on it will actually damage the roof. So I'm very skeptical about warranties. 20 years, I've had ones go 20 years myself. That's possible. 30 years, I don't know. I don't know. Could be. All right, green roofs. This is something, I don't know if you guys have ever dealt with green roofs, but sustainability industry have gone to say that green roofs are a good thing because of the grasses are growing instead of just it lowers the heat island effect. But I tell you, there's a lot of trouble. ASHRAE has one on their headquarters. This is not the headquarters building, but it's very much like this. It looks kind of like this, but what they actually did, what the problem with these green roofs is leakage. Because when you start putting soil and plants on the roof, you're putting a lot of water on the roof, and eventually it erodes to the roof. So what they did is they put all their plants in plastic pans. They built these pans and put everything inside these pans with drains on the pans. It's very clever, very easy to do because it had nothing to do with the roof. It was all on top of the roof. So very good. So green roof issues are leakage, of course, like I just said, and they're heavy. They're very heavy, so the structure must be built for them. Last thing is water. Water will get into it. You put water on top of them. And the last thing is maintenance. And I love this slide. I had to find this slide. And this is I think this is in Europe somewhere. It's a green roof, and they put goats on the roof. The goats can access the roof to keep the grass mown. I thought that's really clever. So maintenance is an issue. You have to maintain these roofs. So you might run into green roofs. So shade and security structures. Shade louvers can shade an area like a glass window or something. Shade screens, which shade also an area, but they're permanent screens. These can be motorized, so they can change. Shade structures in general, just shade a structure. Shade structure issues are shading performance. Thermal bridging, in case the structures are designed to go through the wall or something, they can catch that. Where a structure member bridging is where a structural member transfers heat between the ambient and the building interior. And when you thermal a building, if you have thermal bridging, it shows up right away. So you can see this. So shading structures are designed to improve the thermal transmission of a building. So they are important to us. Normally beams, trusses, and other structures are part of this thermal bridging. The way you cure thermal bridging is, I didn't actually believe it would work, but I had a building that had some large structural members that went outside the building, and then the building wall enclosed them, and it went inside the building. And I was all set to see that, but what they did is they put some special kind of thermal paint on the exterior of the columns and on the interior of the columns. It was just paint, and it cut it immediately. I could no longer see the thermal bridging on the thermal camera, so it was still there, but it was probably 1 or 2 degrees. It was not hardly anything at all, so they do work. Security structures, egress protection structures, pipe bollards to keep people out of areas. We have structural elements that are permanent structure to keep vehicular traffic away from the building. And then we have active structures that are motorized that come up out of the ground to protect a building from egress where it shouldn't be, either from people or from motor vehicles. Air intakes is another thing. We want air that are not accessible to fumes or bioagents. So this is a much harder thing to do. We want to protect the building from natural disasters and from man-made disasters. And natural disasters, we want to make sure that they're designed so that flooding can't get in the building through a louver, or an opening. We want to make sure that wind-driven stuff can't get into it, or we want to protect it from snow and ice from getting in those. But we also want to watch it from man-made. So we want to put a louver where a person can't walk up and throw a biological agent in an intake louver. You got to prevent that. You have to put an intake louver in such a way that that can't be done. It's things we never thought about before, but we need to think about them now. And that's it for enclosures. I hope that information was helpful. Enclosures are a little different than what we normally do, but they're fully understandable. Use common sense, and you'll do good at it. So thank you very much for watching. I hope you enjoyed the video. I hope you have a great day, and I'll catch you on the next one. Thanks.